In this class, we will derive the mass conservation or continuity equation in the differential form and then use it to solve a problem. We will do this in the Cartesian coordinate system. We have already seen the mass conservation in integral form when we are doing macroscopic balances. So, there we used the Reynolds transport theorem to find the mass conservation equation, where we replace the general extensive property n with m and the intensive property eta, which is m divided by m, that is equal to 1. So, again what we will do, we will take a small control volume, which is a differential control volume, we can say, and this differential control volume we will assume it to be of a cuboid form, which have dimensions dx, dy and dz along the x, y, z coordinates. So, we will consider Cartesian coordinate system and then we will derive the mass conservation equation in the differential form for Cartesian coordinate system. We will be able to write it in the vector form, and this vector form can also be used or can be expanded in the cylindrical coordinate system. Okay. So, let us look at this. We have the differential volume or differential control volume. The point at its center is O, which has coordinates x, y and z. So, the point O is at a distance dx by 2 from the x face on the left side and dx by 2 from the left face on the right side, and so on. So, it is at the center of this cube. Okay. Now, this cube, the dimensions are dx, dy, dz. So, the volume of this cube will be not cube, it is cuboid, because the dimensions are different, dx, dy and dz, and they are not necessarily equal. So, we have dv is equal to dx, dy and dz. We will not assume anything about the independence of the fluid or flow properties. So, when I talk about fluid properties, I am talking about fluid properties such as density and viscosity. So, density can be a function of space, that means the density can be different at x, x, y, z 1 1 1 and x, y, z 1 2 3. Density can also be different with time. So, density can be a function of time. Similarly, the flow properties, which can be the pressure, which can be the stress, or which can be the velocity field. So, here when we derive mass conservation equation, we will be concerned with density and the velocity. So, the density and velocity, we will assume that they are function of space and time. Now, let us say that density at this point O is rho, okay, and then we can apply the Reynolds transport theorem or the mass conservation equation in this differential control volume. We will assume that the flow can come in or go from this control volume. Okay. So, the differential equation or the mass conservation equation is del over del T of integral over the control volume rho dV plus integral over the control surface or area integral rho v dot dA. So, now our task remains to evaluate these two terms for the differential control volume that we have considered. So, let us look at the first term of this equation. Now, the first term is basically integrating density over this control volume. So, because the density will be a continuous function, and we can write Taylor expansion for density, and then it will be varying in all the directions. But when we do the summation or the integral over the control volume, then we will have that is equal to rho dx dy dz. So, in this small control volume, the density is rho, which is the density at point O into dx dy dz. When we will be finding out the terms for the second term, or when we will be evaluating the fluxes at different phases, then we will consider the variation of density, because the density will be varying, say for example, x to x plus dx by 2 or x to x minus dx by 2. In this case, because we are taking the integral over the entire control volume. So, so when you take the density at the two symmetric phases, that will cancel out, and finally, you will end up with this expression. Okay. So, you can do that exercise for yourself or to convince yourself. Now, because the first term is time derivative or partial derivative with respect to time of this integral over the control volume rho dv. So, when we replace integral rho dv by rho dx dy dz and take its time derivative. Now, the control volume is not going to change, its boundaries are not going to change, the volume is going to remain fixed. So, dx dy dz can be out of this differential, or this will not be dependent on time. So, dx dy dz come out of the differential term, and del rho over del t remain, because the density can be a function of time, or density is a function of time. We have considered that. Okay. So, that is our first term. Now, we will try to find out the second term, which is the area integral over the control surface. So, for this control volume, all its faces, there are 6 faces in this cube, 1, 2, 3, 4 and 5, 6. So, left and right faces along the x direction, as we can see, top and bottom faces along the y direction, and front and back faces along the z direction. Okay. So, we will need to evaluate the fluxage, which is basically rho v dot dA. So, we need to evaluate each of these terms rho, v and dA for each of these areas, and then substitute in this, so that we can find out the second term. Okay. So, we need to evaluate on the 6 phases the velocity, this velocity vector, let us assume that at point O, the velocity vector v is equal to u I plus v j plus w k, which is the which are the u, v, w are the x, y and z component of velocity at point O. Okay. So, density, we know that at point O is rho, velocity at point O is u I plus v j plus w k, and now we also need to find the magnitude of area vector d A, and the direction will be normal to that particular face, depending on it is x plane or y plane or z plane, and it is pointing out in the positive or negative direction. Okay. So, let us do that exercise, and we will start with the first face, which is shown by a green boundary here. So, this is the right face, and the normal to it will be in the positive x direction. So, it will be I direction, and the dimensions of this face, this is a x plane. So, y z it will be in yz plane. So, this dimension is dy and the other dimension is dz. So, dA will be dy dz into I. Now, we also need to find the density and velocity at this phase. So, the density we can write because this phase is at a distance. So, if we take the center to center distance between the face and the center of this cuboid, that will be x plus dx by 2. So, using Taylor series, we can write an expression for the density at this phase, which will be rho at x plus dx by 2 is equal to rho plus del rho over del x into dx by 2 plus second derivative of rho with respect to x multiplied by 1 over factorial 2 into dx by 2 whole squared and so on. So, you will have terms which are higher order. Now, as we know that we have assumed dx, dy, dz to be small. So, the higher order terms dx squared and higher dx cube etcetera, they will be smaller when we compare them with respect to dx. So, those terms we will neglect. So, we will consider only the first two terms. So, this will give us the density on the right face, which is rho plus dou by dou x of rho into dx by 2. Okay. So, if you look at that is the density at point O plus the variation of density or the density gradient multiplied by dx by 2. So, basically considering the linear variation of density, that is the density on the right face. Now, the area, as we have already discussed, is dy dz I. Next, we need to find what is the velocity vector at this face v dot dA, because the velocity v dot dA, in that the only the normal component of velocity will be relevant, because the other two terms of velocities, when you take the dot product with the area vector which has I, that will become 0. So, we will take the u component of velocity at this face, or x component of velocity rather. So, x component of velocity u small u, that will be at x plus dx by 2, that will be equal to u plus del u by del x into dx by 2, using the same argument that we used for finding out the density. We have done Taylor series expansion for u and then neglected terms dx square or higher powers of dx. So, this is again a linear variation, you can say, of u along x direction. Okay. So, now we know the variation or the density at the face, we know the area vector and we know u. So, at the right face we can write v dot dA in the integral, that will be equal to because the area vector point out normal to the face in the positive I direction and u also pointing out in the positive I direction. So, when we take the integral I dot I will be equal to 1. So, you will have u plus del u by del x dx by 2 into dy by dz. So, now we can multiply density to it. So, when you combine the density and v dot dA, this is what you have. Now, there are two terms in the first bracket and two terms in the second bracket. So, let us multiply and simplify it. So, if you multiply rho with the first term, so you will get rho u, and this is multiplied by dy dz. So, this is your first term. Then you multiply rho with the second term here. So, you will get rho dou u by dou x into dx by 2 multiplied by this area dy dz. Then let us multiply the second term here with the first term. So, you will have u, which is coming from this, and dou by dou x of rho into dx by 2 multiplied by dy dz. Then you will have another term which will be multiplication of the second term of both the brackets. So, you will have dou by dou x into dx by 2 squared into dy by dz. So, again we will neglect the higher powers of dx. So, dx squared, because this term will be 1 or it will be lower than when you compare with the other 3 terms. So, we can neglect the multiplication of these small terms. So, in this we will have 3 terms rho v dot dA. Okay. So, now we have written down rho v dot dA for the right face. So, now we will do the same exercise for the left face. So, the area vector on the left face will be again the magnitude of area will be same dy dz as that of the right face, but the area vector will be pointing outward normal to this control surface. So, now it will be pointing out in the minus I direction. So, you will have the at the left face area is equal to minus dy dz into I. Now, we will need to write v dot dA. So, dA we already found, and v will be pointing out in the positive x direction or the x component of velocity, because when we are taking v dot dA, what we need to find out at this face is x component of velocity. So, it will be pointing out in the positive x direction. So, we will have these two combined, and now the velocity is u plus dou u by dou x minus dx by 2. So, earlier because it was at a plus dx by 2 distance. So, the property was varying or the flow property u was u plus dou u by dou x dx by 2 on the right face. On the left face it is on the minus side or the in the minus x direction. So, you will have u plus dou u by dou x into minus dx by 2 and multiplied by the area. So, this will be equal to minus u minus dou u by dou x dx by 2 into dy dz, that will be v dot dA, multiply by rho. So, rho on this face will be rho plus del rho over dou rho over dou x into minus dx by 2, same as we did for u on the left face. So, the density on the left face will be rho minus dou rho by dou x into dx by 2. We can combine again all this. So, we will get rho v dot dA, and we can take the multiplication and neglect the term which has dx square in it. So, when you multiply the first two terms, you will have rho u dy dz, okay, and a minus sign because of this. Then you can multiply rho with the second term here. So, you will have minus into minus, that will become plus. So, rho dou u by dou x dx by 2 into dy dz. The next term will be product of first term in the second bracket, which is u, into a second term in the first bracket, this term. So, when you multiply, there is a minus sign outside and this minus sign. So, you will have this sign to be plus u dou by dou x of rho into dx by 2 into dy dz. We will neglect the multiplication of the second term of both the brackets, because it will give you dx square, whose magnitude will be smaller than all three terms. So, this is our rho v dot dA on the left face. So, we have looked at on both the faces. Now, one can have a doubt in the mind that we have taken the variation only along the x direction of rho and u, and why not along the y direction. So, as I said, for the density, when we were talking about volume integral, if you take the variation along the y direction, those variations, when you take the summation or the integral over it, they will eventually cancel out, and you will end up with the same thing. Okay. So, next we can do the same exercise for the top and bottom faces. So, that is what we are going to look at. So, let us look at first the top face, which is pointing out along the positive y direction, and the distance of this face from the point O is dy by 2. So, we will have at the top face, the area will now be, because it is a xz plane and pointing out in the positive y direction. So, dx dz, that will be the magnitude of area, and the direction will be positive y direction. So, the unit vector is j. The density there, rho y plus d by 2, because the face is at a distance dy by 2 from center O. So, that will be rho plus del by del y into dy by 2. So, now we are considering the variation along the y direction. Okay. And similarly, the v component of velocity, because now we are looking at the area which is pointing out in the positive y direction. So, the u component of velocity and or the x component of velocity and z component of velocity, when we will have dot product with dA, they will become those terms will become 0. So, we will find only the y component of velocity. So, v at the location y plus dy by 2, which is the top surface, that will be equal to v plus dou by dou y of v multiplied by dy by 2. So, we can write v dot dA these terms and find out rho v dot dA at this top plane. So, you will have rho being rho plus dou by dou y of rho into dy by 2 into v dot dA will be positive, because both the velocity component and the area vector, they will be pointing out in the positive direction. So, you will have v dou by dou y into dy by 2 into the area dx dz, and we can expand the terms and neglect the multiplication of the two second terms. So, because now it will have a dy squared into dx dz. So, again the magnitude of this fourth term will be smaller than the other three terms. So, we will neglect that term. The first term, which will be multiplication of the first term of both the brackets, rho v dx dz. The next term, rho multiplied by dou v by dy into dy by 2 multiplied by area dx dz, and the third term will be v multiplied by dou y of rho into dy by 2 multiplied by area dx dz. Okay. Similarly, we will write the terms for the bottom face, which is this one, and the normal vector will be pointing out in the minus j direction, or the unit vector normal to it will be minus j, and the distance of this bottom face will be at a distance minus dy by 2 from point O. So, we can write the rho v dA individually. So, dA will be dx dz, but pointing out in the minus j direction. Rho will be here rho minus dou by dou y of rho into dy by 2. This minus comes because it is in the negative direction. Similarly, for v will be v minus dou by dou y of v into dy by 2. We will find out, or we can find out v dot dA. One is pointing out in the minus j direction, another in positive z. So, dA minus j and v is positive j. So, when you take the multiplication, you will have minus v minus dou by dou y of v into dy by 2 and multiply by the magnitude of area dx dz, that will be v dot dA, and then we can collect all the terms rho v dot dA and take the multiplication and neglect the term having dy squared. So, then we will have all three terms. You can see the sign here will be, because of this negative, this sign will be minus, then you multiply the first term from here. So, this minus will become plus. So, remaining two terms become positive, but the first term becomes negative here. Okay. So, now we have done the fluxage, or we have obtained the mass flux at x phasage and y phasage, and we are left with the two phasage along the z direction, front and back phasage. So, we can do the similar exercise at the front face here. So, at the front face, which is at a distance of dz by 2, and the unit normal is pointing out in the positive k direction here. Okay. So, the area vector will be dx dy, because it is a xy plane, dx dy into the area vector or the area normal, unit normal k there. It is in the positive z direction. So, rho at this face will be rho plus dou by dou z of rho into dz by 2. Same for w plus dou by dou z dz by 2, and we can combine all this together. So, we will have a rho, which is rho plus del rho by del z dz by 2, w plus del by del z of w dz by 2 dx dy. And when we do that, because both the vectors are pointing out in the positive direction, so their dot product will be positive. So, we can now write down the first term will be rho w multiplied by area dx dy. The next term will be rho dou by dou z of w dz by 2 into dx dy, and the third term will be w dou by dou z of rho into dz by 2 into dx dy. The fourth term, which will be multiplication of these two small terms, that we will neglect, because that will have dz squared, and the term will be smaller in magnitude when you compare with these three terms. The same exercise for the sixth phase, which is at the back at a distance of minus dz by 2 from point O, and the normal to it will be pointing towards minus k direction, or the negative z direction. So, the dA will be dx dy into unit area vector or unit vector k. Rho will be at z minus z by 2 will be the z coordinate on the back plane or the back face. So, that will be rho minus dou by dou z g by 2. Similarly, w will be w minus dou by dou z w into dz by 2, and we can write all this. V dot dA will be negative, and we combine all the terms. So, the multiplication will be minus rho w dx dy plus rho dou by dou z into dz by 2 dx dy, and the third term will be minus will become plus w into dou rho by dou z into dz by 2 into dx dy. So, now we have this integral rho v dot dA on all the faces, and we can sum all the sum this term to find the second term in the mass conservation. So, which is integral over the control surface which has 6 faces rho v dot dA. So, we can write all the 6 terms that we have obtained, the 2 terms for x faces, the next 2 terms for y faces, and the last 2 terms for z faces. So, we can see that the first terms here, in each case they are positive and negative on the respective, say, left and right faces, positive and negative, top and bottom, and front and back. So, the first terms in all the brackets will cancel out, and we can put together all these terms and try to see what do we get. So, if we look at, you have the second term of the brackets on the left and right faces, you have same terms rho dou u by dou x dx by 2 dy by dz. So, when you add them together, you will have rho dou u by dx, dx by 2 plus dx by 2 will become dx into dy dz. Similarly, the next term, which is u dou rho by dou x into dx by 2 dy dz in both the places. So, dx by 2 other components being same. So, you will have dx by 2 plus dx by 2 will become dx. So, the next term will be u dou by dou x dx dy dz. Similarly, when you combine the second term for the y faces, then you will see you get rho dou by dou y into dx dy dz. The last terms, when you combine them, you will get v dou by dou y dx dy dz, and doing the same thing for the front and back faces, you will get rho dou w by dou z dx dy dz plus w dou rho by dou z dx dy dz. Okay. So, let us see if we can further simplify this. So, this is the summation or the integral over rho v dot dA. So, if we combine this, then we see first that all of these, all 6 terms will have dx dy z dz. So, that can come out, and now we have 6 terms rho dou u by dou x plus u dou rho by dou x plus rho dou by dou y of v plus v dou by dou y of rho plus rho dou by dou z of w plus w dou by dou z of rho. Okay. So, let us look at the first 2 terms here, and that is nothing but when you expand dou by dou x of rho. So, if you write dou by dou x of rho u, then the first term, when you expand it, the product of this differentiation. So, you will take rho as it is and the differentiation of u. So, rho dou u by dou x plus u dou rho by dou x. So, the same thing you can see, the next 2 terms will be dou by dou y of rho v, and the last 2 terms will be dou by dou z of rho w. Okay. So, we can write this. So, we will have now dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w multiplied by dx dy dz. or if you look at this term carefully, then this is basically del operator operated on rho velocity. So, if you remember, the del operator is I dou by dou x plus j dou by dou y plus unit vector k dou by dou z, that is del operator, and take its dot product with rho v. So, dot product with rho u I plus rho v j plus rho w k. And when you do this exercise, only I dot I, j dot j and k dot k will be non-zero, other multiplication terms will become 0. So, you will have I dot I. So, dou by dou x of rho u, that is your first term, dou by dou y of rho v, second term, dou by dou z of rho w. So, you have you can write this in terms of vectors. So, del dot rho v dx dy dz. Okay. So, let us, we have found the first term and second term and put them together. So, the first term in the mass conservation equation was the partial derivative with respect to time of integral, volume integral of rho dv, and the second term the surface integral over the control surface of rho v dot dA, and we have simplified. So, first term is dx dy dz rho del dou rho by dou t, and the next term is del operated or del dot rho v into dx dy dz. So, let us sum those together. So, you will get the mass conservation equation, and you have dx dy dz. So, we can divide by dx dy dz, and the equation in vector form we will get is dou by dou t of rho plus del dot rho v is equal to 0, or if you expand it in the Cartesian coordinate, you can write del by del t or dou by dou t of rho plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. It is easier to remember in this form, and it is useful to remember the continuity equation when you are studying a fluid mechanics course. Okay. So, we can look at some of the variations into it. This is also called continuity equation, and we already saw that this del is in Cartesian coordinate, we can expand it in this manner. If the flow is steady, so we know that the steady flow means that the density is not going to change with time, the velocity is not going to change with time. So, the first term dou by dou t of rho is equal to 0. So, we will have a dou dot rho v is equal to 0, or you can write in the expanded form. Now, another variation we will look at, say if the flow is incompressible. So, when the flow is incompressible, then the density is constant. So, again the first term will become 0, dou by dou t of rho is 0, because rho is constant, and now rho is constant. So, it does not depend on x, y and z coordinates. So, this can come out of the bracket. So, you will have basically rho into del dot v is equal to 0. So, you can divide by rho, which is a constant, and you have del dot v is equal to 0 is your continuity equation for incompressible flow, or if you expand it, then you will have dou by dou x u plus dou by dou y v plus dou by dou z w is equal to 0. So, for an incompressible flow, the first term will anyway be 0 if the flow is steady or unsteady, and because we will be dealing with incompressible flow most of the time in this course. So, del dot V will be the thing that we will be using. If the flow is unsteady, again the first term becomes 0, but then rho is not necessarily, because we have said that if the flow is steady, it is not necessarily incompressible. So, if the flow is compressible, then rho can still be a function of x, y and z. So, the equation will be del dot V as we saw in the previous slide. So, that is the difference in the two variations that we saw for steady and incompressible flows. Now, let us look a simple example. So, we consider a piston cylinder system as shown in the figure here. At one instant when the piston is at a distance L0 away from the closed end of the cylinder, the gas density inside the cylinder is uniform, which is rho 0. So, let us say that this particular instant that one is talking about is T naught or T 0, and the piston begins to move away from the closed end at a speed constant speed u. So, at T 0, at T is greater than T 0, the piston starts moving with a speed u. Okay. Assume the gas velocity inside the cylinder to be one dimensional and proportional to the distance from the closed end. So, the gas velocity inside the cylinder is proportional to the distance from the cylinder, and what we need to find is an expression for the average density of the gas in the cylinder as a function of time. So, if we look at this flow, the flow is not steady, because the density when it is expanding, the volume is expanding and the flow or the gas is inside the system. So, it is going to change with time. So, the flow is not steady and density is also not constant. So, flow is not also incompressible, okay, but the flow is one dimensional, it says, and the density in the cylinder can be assumed to be uniform. So, that means that rho is a function of rho t only and is not a function of x, y or z. Okay. And gas velocity varies with x. So, it says the gas velocity, the flow inside the cylinder is one dimensional, but the gas velocity varies from its a gas velocity inside the cylinder to be one dimensional and proportional to the distance from the closed end. It varies linearly from 0 at the closed end. So, the velocity is 0 at this end. So, it will be varying. So, this will be 0 here and it varies up to the piston. So, at the piston that will be equal to the piston velocity. So, we can write down that at any point of time what is the distance between the piston and cylinder, because that is varying. So, let us say that this distance in general at any time is L, and at time t is equal to t 0, the distance is L naught, and then it moves with a constant speed u away from the piston. So, that will be L is equal to L naught plus u into time, and that time will be t minus t naught. So, that is the expression for the distance between the closed end of this cylinder and the piston at any time t is greater than t naught. We can see that at time t is equal to t naught, this will give us L is equal to L naught. The gas velocity we can find now the gas velocity, because gas velocity is proportional to x direction. So, we can write this u is equal to x by capital L. So, it is proportional to x and multiplied by u by L. So, it will become 0 at the closed end, and at the piston, that will become equal to x is equal to L at the piston. So, it will become equal to piston velocity, gas velocity at the piston. Okay. So, now this L is not a constant, it is a function of time. So, we can substitute L from here. So, that will be u x divided by L naught plus u t minus t naught, which is the expression for L. Okay. Now, we can substitute this in the mass conservation equation. So, let us write down the differential form of mass conservation equation. Dou rho by dou t, because we need to find the variation of density with time. So, we can use this equation, and the flow is one dimensional. So, that means the y component of velocity, which is v, and z component of velocity, which is w, both of them are 0. The density is uniform in the cylinder. So, rho is not a function of x. So, we can write this equation or simplify this equation, this term, the third term and fourth term, they become 0, and you can write dou by dou t of rho plus rho dou u by dou x. Rho can come out because rho is not a function of x. So, rho can come out of the differential or differentiation. Okay. So, now we already had a function of u as a function of x. So, we need to find dou by dou x of u. So, we can differentiate u with respect to x. So, dou by dou x of u differentiate with respect to x, the denominator is not a function of x. So, that will be equal to u divided by L naught plus u t minus t naught. Now, you can substitute it there. So, we can substitute dou u by dou x in the continuity equation, and because rho is a function of time only. So, this can become, this is a partial derivative, but rho is a function of time only. So, we can write as a total derivative d rho by dt now. Dou rho by dou t becomes d rho by dt plus rho times dou u by dou x. So, we can substitute the value of dou by dou x of u, which is u divided by L naught plus u t by t minus t naught, and we can integrate this equation to simplify. So, first we can take the variables on the each side. So, rho becomes, so the left hand side can become d rho by rho, that will be equal to minus u times dt divided by L naught plus u t minus t naught, and we can integrate it in the limit from time t 0 to t, and at time t 0 we know that the density is rho naught, and at time t we can say the density is rho. So, we will get rho as a function of time. When you integrate, the first term d rho by rho will be ln rho, and substituting the limit we will get ln rho by rho naught. The next term, when you integrate it, will be minus u, and when you integrate this term, so you will get 1 over u ln of this term. So, you will have minus ln of L naught plus u t minus t naught, and the limits from t naught to t. So, when you substitute limit as t, you will get L naught plus u t minus t naught, and at time t naught the second term will become 0, because t naught minus t naught is equal to 0. So, you will have divided by L naught only. So, you have ln on both sides, and there is a negative sign there. So, you will have rho by rho naught is equal to 1 over this term, or this term will be reversed. So, you will have rho by rho naught is equal to L naught divided by L naught plus u t minus t naught, or rho is equal to rho naught L naught divided by L naught plus u into t minus t naught. So, this example we had the flow to be unsteady and compressible, and we used a one dimensional differential form of continuity equation. I think we all of us who are taking this course, we should remember the differential form of continuity equation, which is dou by dou t of rho plus del dot rho v is equal to 0. Okay, let us stop here. Thank you.